Okay, here are a few more example video or example problems. So Kyoko had $10,000 that she wanted to invest. Her bank had several investment accounts to choose from, all compounding daily. Her goal is to have $15,000 by the time she finishes graduate school in 6 years. To the nearest hundredth of a percent, what should her minimum annual interest rate be in order to reach her goal? All right, so what do we know? Well, we know she has 10,000 to invest, so that's going to be our P. Her goal is to have 15,000, so that's going to be our A of T. Time, she said, in 6 years. And she's compounding daily, so N is equal to 365, and we're looking for R. Okay, so we plug all that in. We have 15,000 is equal to 10,000 times 1 plus R over N, which is 365, times N, which is 365, times the time, which is 6 years. Okay, now we need to solve this. And so how do we do that? Well, first we're going to divide by 1,000 on both, 10,000 on both sides. Okay. And so then that gives us 1.5 is equal to, and then we have 1 plus R over 365. And then if we multiply that out, that's going to give us 2190. Now to get what's in here, we have to take the 2,190th root of both sides, or basically take both sides to the 1 over 2190. Okay. So when we do that, we have the 1.5 to the 1 over 2190 is equal to 1 plus R over 365. Okay, well, now we can keep doing on that. So we'll have the 1.5 to the 1 over 2190 minus 1, because we're going to subtract 1 from both sides. Okay, and then that's equal to R over 365. Now to get rid of this, we're going to multiply both sides by 365. And so then R is just going to be what that is there. And so now what we have to do is plug all that into our calculator. All right, so that was equal to 365 times, now if I remember what we had here, we had 1.5 to the 1 divided by 2190, and then in parentheses, and then down, and then minus 1 in parentheses, and so that should be our rate. And so 6758, so 0.06758, move the decimal 2 to the right, that's going to give us 6.758%, and they want it to the hundredth of a percent, so that would be 6.76%. So that would be the rate that she should get to be able to reach her goal of $15,000 in 6 years if she invests that $10,000. Okay. So that was one a little more complex. You had to, have higher fractional powers, and then we also had to do all the algebra to get to that point. But again, nothing hard, nothing we haven't been able to do before, or you shouldn't be able to do. All right, so our next one here says, so for each year t, the population of a forest of trees is represented by the function a of t equals 115 times 1.025 raised to the power t. A neighboring forest, the population of the same type of tree, is represented by b of t, so that way we can differentiate them, a and b, equals 82 to the times 1.029 raised to the power t. And we need to round answers to the nearest whole number when possible. All right, so which forest population is growing at a faster rate? Well, remember, how do we figure out which one's growing at a faster rate? We look at that growth factor, and so that's the growth factor because we raise that to the power. And 1.025 versus 1.029, well, B of t is growing at a faster rate because it has the higher growth factor. Okay. Now, which forest of trees has a greater number of trees initially? Well, remember, it's A times the growth factor power. So this is A, and this is A. Well, this one has a higher number of trees initially. So A of T has a higher number of trees initially. Okay. Now you could figure that out. Take 115 minus 82, and we get, by 33 basically. Okay, so we can have that value. Okay. Now, continuing on with the same problem, it says, assuming the population growth models continue to represent the growth of the forest, which forest will have a greater number of trees after 20 years? Well, what we have to do is we have to find out what A of 20 is and what B of 20. Well, A of 20, remember, that was the 115 times 1.025 raised to the power 20. And this was, what was it, 82 times 1.029 to the power 20. All right, so we plug both of those into our calculator. And again, just a matter of can you manipulate your calculator? So we have 115 times 1.025 to the 20th. And so that's 188.44. And the other one was 82 times 1.029 to the power 20. And so that's 145.25. So that's our two values. And so that was, what was that again? 188.44. And that was 145.25. And so, if we subtract those off, there's going to be a difference of 43 because that's going to be the 188, that's going to be the 145, and so that's 3 and that's 4. So there's 43 more trees in A. Okay, so that's how we would do that one. So we round it to the nearest whole number, round that to the nearest whole number, and we have a difference of 43. Now with the 100, the only difference we do is we say, well, it's A of 100 instead of A of 20, and we plug in 100 here, and then B of 100 is 82 times 1.029 times 100. All right, and so we plug in those values. So if we do second enter, that will give us this one. And so we have 1430. And if we do second enter, and then plug in 100 here, that's 1358. So 1430.05. So that's going to be 1430.050, and that was 1358.577. And so this one is going to be, let's see, how if we subtract those, that's going to be, well, if we round them, it's going to be 1430. That's going to be minus 1359. And so that's going to give us, what, 71 trees difference? And this one, B, is going to be larger. Okay, so if we look at this, up until, even year 20, A was larger because it started out with a larger number. Their factors are close. This one's larger, so it's eventually going to get bigger. But at 20 years, A is still bigger. Now, even though it starts out larger, it ends up being smaller once we hit that 100 years. Now, we could figure out where that crossover point is, but we're not going to do that for now. And then we have a lot more trees at this point in time than we do at this point in time. And so, and this one's going to just keep growing and growing bigger and bigger as we go. But the key thing is there's a certain point, there's so many trees you can fit in a forest, and so that'll be a problem. There's going to be conditions of water, there's going to be conditions of that. So do the growth models continue on past 100 years? And so there's a lot of things that might not actually continue on past that point in time, but up at 20 years and 100 years, assuming that that growth model continues to represent it, then those are what we find. A of t is at 20, B of t is at the 100. All right. So here what we're going to do is we're going to look at values of cars. So we're going to do depreciation. And so a car was valued at $38,000 in the year 2007. By 2013, the value depreciated to $11,000. Now, if the value of this car continues to drop by the same percentage, what will it be worth in 2017? Well, we know that in time zero, t of zero, that's going to be $38,000. And then what we're going to do is we're going to move up to the next year. Is going to be in 6 years. So t of 6 is going to be $11,000. And so then what do we know without that? Well, we can actually calculate what our value is because we know that this is 0, 38,000, and this is 6, 11,000. And so we can say, well, 11,000 is equal to 38,000, then b to the x, which is 6. So we divide by 38,000, divide by 38,000. And so then we have 11,000, or we can even just drop the zeros here. We don't even have to keep all those zeros. And so we can have 11 over 28 equals b to the 6th. And so we solve for that. We take to the 1/6, and we take that to the 1/6. So 11 over 28. And we'll better put that in parentheses. So insert a parenthesis there. And that's to the power 1 divided by 6. And that looks like it should work. And so we get, oops, that's 38, not 28, sorry. All right, so we get 0.813333. So that's what our B is. And that's a 3 there too. It looks like a 2, but it's a 3. And that's a 3. I noticed that because I saw that. All right, and so B is equal to 0.813333 and so on. And so we have the function of basically a of x, but now let's see, what do we want to do? We want to find at 2017, which is 10 years later, so we want a of 10 is equal to 38,000 times b, which is 0.81333 up to the power 10. Okay, so now we can plug that in. So we're going to take that number basically, and we're going to raise it to the 10. Then now we're going to remember to bring it down, and we're going to multiply by that 38,000. And so that's how much it's going to be worth in 10 years based on the model where we found the B and plugged everything back in. So 48, 13, 55. So that's what the car will be worth in 2017 based on the exponential decay model that we found from 2007 to 2013 and then extending on to that 2017. All right, so this one's going to be a little more complex. So we have an investment account with an annual interest rate of 7% opened with an initial deposit of $4,000. Compare the values of the account after 9 years when the interest is compounded. So we're going to have to compound it annually, quarterly, monthly, and continuously. So we're going to have a bunch of different values we're actually going to have to calculate. So all we're going to do different in those is depending on what the N is. So for the first one, we're going to have our A of t, and t in this case is 9, so we're just going to plug it in automatically. A of 9 is equal to our principal, 4,000, times 1 plus r, which was 0.07. Again, we always have to convert to decimal, over n. So first one we're going to do is annually, so it's n is 1. And so then it's going to be raised to the power n times t, and so we'll get a value out. 2. A of 9 is equal to 4,000 times 1 plus 0.07 over quarterly, that's 4. And then that's going to be raised to the power 4 times 9. Okay, 3. A of 9 equals 4,000 times 1 plus 0.07 over monthly. Well, there's 12 months, so that'd be 12. And then 12 times 9. And continuously, remember that's PERT. So A of 9 equals 4,000. E to the R, 0.07 times T, which is 9. And that will give us the value there. And so now all we have to do is plug all those into our calculator, and we can write them down. And so the cool thing with calculator is, let's clear all that so we can see it all at once. We're going to have 4,000 times 1 plus 0.07 divided by the first one was annually, so that's a 1. And then that's raised to the power, and then we'll have 9 times 1. Now I'm changing the order here because then I can make things a little easier. And that gives me the first one, 7,353.84. Okay, so I'll write that down. And then we will go back and we'll say, okay, well now we're doing quarterly. So we have to divide by 4 here, and I have to multiply by 4 here. And so now I have that much money, 7,469.63. Okay, so I'll write that down. Okay, now I'm just going to go back in again. And now instead of 4, I'm doing monthly, which is 12. So I'm going to have to insert, I'm going to put a 12 there. And over here, that's going to be a 12. I have to extra parenthesis. And so that's 7,496.71, and that's going to be my value there. And then my last one is going to be different because I'm doing a continuous, so I'm going to take 4,000 times E, and it's going to be raised to the power 0.07 times 9. And of course, that one should be the biggest, 7,510 and 44 cents. Okay, so let's write those back down over here. And our first one we found was 7,353.84. Our second one we found was a little bit bigger, 7,469.63. The next one's a little bigger. It was 7,496.71. And our last one, which we'd expect to be the largest, was 7,510.44. Okay, and so those are the possible choices. Now, if I was to invest it, I would probably do this one right here, because that would give me the best interest return, give me the largest value for my money. All right, so that's all I have for you on the extra videos for today.